example. Now we said that if we have this rod, if it's moving with a velocity v, there will be a current running through the circuit. We will study that current later on. But if there is a current running through it, there is a resistor over here, so the resistor will be dissipating some energy. So where does that energy come from? So we have our closed system. The wire is our closed system, let's say. So as time goes on, our system is losing energy through this thing. So where does that energy come from?
Kinetic energy of the rod.
So there is a hypothesis over here. The rod has a kinetic energy initially. So as the rod is moving, this kinetic energy of the rod should decrease due to some reason. And so if it is to decrease, there should be some force acting on it. Now let's look at what is the force acting on a wire in a magnetic field. Now we know the forces acting on charges. So let's assume we have a wire of an arbitrary shape. It doesn't have to be straight. It is carrying a current I. So here there will be charges moving. Let's say a charge dq. Moving in that direction. Now let's just take a very small segment of our wire. This is dl. This vector is our dl vector. We take a very small segment of the wire. In the wire, in this segment, there is a charge dq, and it's moving. The charges are moving with the drift velocity vd. And let's also assume that there is the cross-section of the wire here is A. There's a cross-section of the wire. Now the force acting on this, what is the force acting on this wire? This segment of the wire? Now what we are doing is we are taking a very small segment of the wire. The length of that very small segment is dl. We also define a vector dl that is along the wire. It's in the same direction as the current, which we will be using later on. Now in this segment, there is a charge dq, and the cross-section area is A. The density, we can also, let's say, n is the number density of the charges. But anyway, we already know that the force is nothing but the dq times the velocity of the charges, which is v cross b. V is in this sense, it will be the drift velocity. Do you agree? What is D? There's some magnetic field somewhere in some direction. B is non-zero. If B is zero, the force is zero anyway. I don't really know the direction, but I don't need to know the direction. Everybody agrees? Now, let's try to relate this to the current. Let's assume that we choose this segment, we choose a time dt such that the drift velocity multiplied by dt is equal to dl. So this basically, if we wait a time dt, all the charge in this segment passes through this area, because this segment has moved by its length. So if it was at the beginning, if it was at this position, after this time dt, it is now over here. So all this charge moved through this point in a time dt. But we know the definition of the current. I is nothing but dq by dt. This is the current we have. So if we just put it over there, df will be equal to dq by dt times vd times dt cross b. Well, dt's, they just cancel. I just multiplied by dt divided by dt. So I didn't do anything. But due to this definition of dt, this is how I define dt, by the way. This is the definition of dt. We know that this is equal to the current. And this is nothing but the length of my segment. So this is the force acting on a very small segment of current carrying wire in a magnetic field, I times dl cross b. Do you agree? So what we assumed is we take a current carrying wire, which can have an arbitrary shape. We just considered a very small segment of the wire. This is the force acting on this very small segment of the wire. I is the current running through my wire, it's the same everywhere. And this dl is the length of this segment. B is the magnetic field at that point. By integrating by just summing over the forces acting on each one of the segments, we can calculate the total force. No, the force, we calculate the force. And from the force, if there's some motion, etc., we can talk about the work done. But let's go to the previous example. There are a couple of things. I mean, we had a hypothesis. We had a problem. We said that, okay, if we start this, if we have this rod, we just set it in motion with an initial speed v. We said that if we connect it to a circuit, there will be a current running through it in the counterclockwise sense. Because, no, in the clockwise sense. The electrons will be pushed downward, so the current will be running in the clockwise sense. But if there is a current running through the system, through this resistor, it will be dissipating some energy. So the question was, where does that energy come from? But then there was this hypothesis that that energy mainly came from the kinetic energy of the rod. So if that is true, then the speed of the rod should be lowered. I mean, it should get slower and slower. Does it get slower and slower? So we already know that if this is our system, there is a current running through our system, I. So this is the direction of the current, I. And remember, df is equal to I times dl cross b. dl, for each segment, dl vector is pointing upward. What is dl cross b? In which direction is dl cross b? dl cross b is towards the left, so it is slowing it down. So kind of, it seems to be consistent, the hypothesis. Of course, we still have to calculate the energy dissipated and relate it to the change in the kinetic energy of the rod. There's still some more work to do, which we will do it eventually, but at least it seems that things are consistent. When there is a current running through the system, the force acting on my rod moving in the magnetic field is in the direction to slow it down. So its kinetic energy will be lowered. So kind of energy conservation seems to be saved. Now let's apply it, the force on a straight wire. In a uniform magnetic field. So let's just say we have a magnetic field, again pointing into the screen. And let's assume we have this rod carrying a current I. Just like in our example. But this time this rod, we can take it infinite. We don't really care what it does. The question is, what is the force acting on unit length of this wire? Now, what we need to do is, as some of you had pointed out, we already know what the force is acting on each one small element. We can just sum them up or integrate them over to obtain the total force. Now, dF is equal to I times dl cross B. Now, let's just choose some axis. X, Y, Z is pointing upward. What is the direction of dl cross B? Minus x. So it is I times dl times b. The angle between them is 90 degrees, so sine of 90 is just 1 in the minus x direction. Or df cross dl, this is the force per unit length, is nothing but I times b in the minus x direction, in some direction. Or we can even write this as if we define such a vector, the current is not a vector, the current is a number, but here I'm just defining this vector, which I use the same symbol, and if I define it, I can just write it in this form, the force. Okay, any questions? Now I will be using this result in another example. Now let's just imagine we have a rectangular loop. We have a region of space which has a uniform magnetic field. And in this region of space, we put a rectangular loop something like this. So that's basically, let's imagine the magnetic field is pointing in this direction. I have this rectangular loop, the edges, so I put it like this. This is my shape. This is the direction of the magnetic field. This is the loop. If I just look at it from the side, what I will see is these are the magnetic field lines, and I will only see this straight line over here. So that will be easier to draw for me. I just see the side. Now, this is the direction of the magnetic field. The current is running like this. At the top part, on this line, the current is running in this direction. That will be my definition. Into the screen. So the current is running into the screen in the top part, out of the screen in the bottom part. The magnetic field lines are pointing in this direction. So what is the direction of the force acting here on this side? I is in this direction. Magnetic field is like this. I, B is over there. You say, this is I. This is B. I is into the screen. This is B. I cross B. This is DL. DL cross B is pointing downward. So the force at the top is pointing downward. Does everybody agree? Now the force at the bottom, again, this is my rectangle. At the bottom edge, this is the direction of the current. The current is running like this. So what is the direction of the force? This is B, this is DL, this is the direction of the current. DL cross B, it's pointing upward. This is the force acting on the bottom. Now, what can you say about their magnitudes? Let's say this has side A, this is B. So what can you say about the magnitudes? What is the angle between DL and B? This is my DL, this is my B. What is the angle between the two? 90 degrees. This is my DL, this is B. The angle between the two is just 90 degrees, so sine of 90 is just 0, 1. So the F top is nothing but I times B. This is the force per unit length. But the length of the top part is A. So this is the force acting on the top. And similarly, the magnitude of the force acting on the bottom is again exactly the same. It's just the directions are different. Now let's say we have four sides of my loop. We already calculated the forces at the top, at the bottom. What about here? What is the direction of the force? You see, the current is running in this direction. On this side, it's running like this. This is the direction of B. So I cross B, it is into the screen. The force acting on this edge, on the edge that is closer to you, let's say this is going in, this is going out. This is B. So the force acting on this edge is in this direction. F closer. I draw it over there. Now let's look at the force acting on the other part. You see, in this part, the current is running upward. In the other part, the current is running downward in this direction. This is I. This is B. I cross B, the current is towards you. In the further edge, this is the direction of the force. And again, they have the same magnitudes. The only difference between the forces, the only reason that the forces are different in this edge and in the other edge is that the current is running in opposite directions. So the forces are just pointing in opposite directions. They have the same magnitude. Okay, so let me ask, what is the total force acting on my rectangular wire? The total force is 0. Because the force acting on this edge and the force acting on this edge, they are identical, but they are pointing in opposite directions. Similarly, the force acting on this edge and the force acting on this edge, they are also identical, just pointing in opposite directions. The force is 0. What about the torque? There will be a non-zero torque, because if you remember, we had calculated that this part, the top edge, is being pushed down. This edge is being pushed up. So it will try to rotate. The forces will not accelerate the center of mass, but nevertheless the forces will try to rotate my loop, current carrying wire. The forces on these sides, they don't create any torque because they are just straightly head-on-head in opposite directions. So they will be passing through the center of mass, so they don't create any torque with respect to the center of mass. Whereas the forces acting on the top and the bottom, they will create some net torque with respect to the center of mass. Now the next question is, what is this torque? First of all, what is the direction of the torque? These are the forces. Well, these two are the forces that will be creating a torque on my system. And what is the direction of the torque created by these two systems? It will be, remember, the definition of the torque is just R cross F. For this point, R is the vector connecting the center of mass to that point. This is R. This is the direction of F. So R cross F is just pointing towards you. So the torque created by this one, and similarly the torque created by this one, they will both be pointing towards you. The total torque acting on my wire will be in the Z direction with some magnitude. Well, the magnitude will be just the sum of two torques, the torque due to the top force acting on the top plus the torque due to the bottom. What is the torque created by the force acting on the top segment? Let's just give some name. Let's call this angle theta. Well, the magnitude of the torque is let's say this is the center of mass. The distance from the center of mass is B over 2. This is the magnitude of R. The force, we had already written the magnitude of the force, that is IB times A. Sine of the angle between R and F. Well, this is my R. This is my F. The angle between the two is pi minus theta. So sine of pi minus theta. Do you agree? Let's write the torque due to the bottom part. What is the torque due to the bottom? This time, this is my R vector. The length of R vector is, again, B over 2. The force has the same magnitude. This angle over here is again pi minus theta, the angle between R and F. So sine of pi minus theta. So we can write the total torque acting on my object as I times A times B times B times sine theta in the Z direction. Do you agree? Again, the sine of theta. Well, we have a vector. We are multiplying it with another vector, with a sine of some angle. And we are obtaining something which is in the Z direction, but Z direction is perpendicular to B. You see in our configuration, B is in the X direction. So B is in the X direction. The torque vector is perpendicular to B. Its magnitude is proportional to the magnetic field times sine of some angle. So it's again almost like a vector product. So if you remember the vector product, the magnitude of a vector product is the product of the magnitudes of the vectors multiplied with sine of an angle. And the vector product is perpendicular to both of the vectors. So here we have a vector tau, which looks like a vector product, It is perpendicular to B. It has some sign. But we are missing the second vector. So let's invent it. Now I will invent a vector, which I will call mu. Mu will have the magnitude equal to I times AB. By the way, what is A times B? Area. So mu is nothing but the current times the area of the loop carrying the current. That is how we define this mu. And the direction of this mu will be, let's see, this is the direction of the mu. Now I will explain why I chose that direction of mu in a moment. But let's see, if I define such a mu, can I write the torque as a vector product? Let's first see that. You see, this is B. This is mu. If we look at mu cross B, let's look at the magnitude. Now, what is the direction of mu cross B? Okay, this is mu. This is B. Mu cross B is towards you. So that is the Z direction. So mu cross B is one thing, it's in the Z direction. Now let's look at the magnitude of mu cross B, which is the magnitude of mu times the magnitude of B times the angle between the two. Now this is mu, this is B. The angle between the two is this angle over here. So what is that angle? Phi minus theta. So mu cross B is nothing but I times AB times B sine theta in the Z direction. But this is nothing but my torque vector. So if I define this mu, then I can write the torque vector as mu cross B. Okay, mu, the name is the magnetic dipole moment. This is the magnetic dipole moment. Well, it is perpendicular to my area. So you see, this was my loop, and I defined the mu to be pointing in that direction, perpendicular to my area. Always perpendicular to the area. Why in that direction? You see, before we also defined area vectors. It was perpendicular to the area, but we didn't choose a direction. I mean, we could have used both of them. Now we have a particular choice, this one. Now the question is, how do we choose that one? You see, the current, there's a current running through my wire, right? My current is running like this. And from your perspective, that is clockwise. Again, use your right hand. Take your right hand, curve your fingers in the direction of the current. That is the direction of this mu. So you just curl your fingers in the direction of the current running through the wire, then your thumb points in the direction of mu. That is how we choose mu. So basically, the direction on the edge, the current has a direction. A direction on the edge already chooses the direction of my area by the right-hand rule. So this is what we call the magnetic dipole moment, and this is the torque acting on the magnetic dipole moment. Now there was a question, why do the charged particles, as they go towards the North Pole, they feel a force? That just reverses their direction of propagation. You see, if you have a charge that is circling a loop, yeah, that is what the charges are doing, right? There is this magnetic field line. They are just going around circles. But if they are going around circles, you can just treat it as an average current running through this circle. So there's a current running through this circle. The circle has an area, and hence the circle has a magnetic dipole moment. So there will be a torque acting on this magnetic dipole moment, but there will also be a force acting on it. You see, now we said that the force acting on this magnetic dipole is zero because the force acting on the top cancels the force acting on the bottom, and the force acting on the sides, they cancel each other. Well, this cancellation happens only if the magnetic field at this edge is equal to the magnetic field at the other edge, and the magnetic field at this edge is equal to the magnetic field at this edge. Only if there is a uniform magnetic field, the forces just cancel each other. But if I don't have a uniform magnetic field, in that case, the magnetic field at the top might be larger or smaller than the magnetic field at the bottom. But if there is such a case, then the magnetic field will exert a net force on my dipole. Well, you see, if the magnetic field lines are approaching each other, that's not a uniform magnetic field. It's a non-uniform magnetic field, hence at different points there will be a different magnetic field strength. So if you put a dipole in such a region, the dipole will feel a net force. And in the case of these particles going to the north and the south pole, the force just turns out to be in the opposite direction to their motion. So they just go up and down. Questions, or too tired to ask questions? They what?
Lighting the charge. I understand why they go up and down, but what causes them to light up?
Now we will see that accelerated charges, they emit light. That is one effect. The second effect, you have a concentration of these these particles, they are not so concentrated. So they are spread over all Earth when they are coming in our direction from the sun. But when they reach these regions, all of them go to 2 points. So there you also have a concentration of them. And they will be also hitting the molecules in the atmosphere. And that is another cause, another reason why we have the lights. So it's all these charged particles going to the poles that is creating these lights. Now, why do the charged particles create light? We will see it at the end of the semester. Questions? Well, all of you look so tired that I just feel like torturing you continually. Yes, questions?
We're trying to digest it and just introduce yourself. So let's take some time because at the moment we're not quite sure what we didn't understand yet.
Okay, today I will end the lecture early. And I just don't feel like continuing with all of you so tired. Now, on Wednesday, you can ask your questions if you know what you didn't understand. You will get the homework, and your pre-report will be chapter 29. No, 28, we already finished. You're not asking questions. So some of you already didn't do the pre-report because they thought that chapter 27 we had already covered. Okay, so if you have questions, prepare them for Wednesday.